right. So, here is what we call, we're dealing with today what we call natural logarithms. So just like regular logarithms, they are basically the inverse of an exponential function, but natural logarithms are a special type of logarithm. They are represented by the letters ln. Okay, natural logarithm, that's what ln means. So when I say natural logarithm, that's what I'm talking about. So it's the same thing as a regular log, except for it always has the same base. So you know how with regular logs, we only assume the base is 10 if there's not a base written in there? Natural logs will never have a base other than e. Okay, e. Do you guys remember e when we did the PERT formula with exponential growth and decay, all that stuff? That's the same e, Euler's number. Okay, it's about 2.7. And we use that to model things in nature. So that's why it's called the natural log. So the natural log is basically the inverse of when we have an exponent with a base of e. All right? So it's going to reverse it just like with regular logs. Okay, so all we're going to do right now is we're just going to practice converting from exponential form to logarithmic form with the natural log. Okay, so let's go ahead and do that. So just like the same skills we have already learned about, here's how you do it. So ln is like your new log. It's going to be base, of course, whatever your base is, of what? Of 9 equals what? X. Okay, that's how you would convert it from exponential to logarithmic form. It's just a natural log. Now, remember how I said that ln always has a base of e. So you actually don't often see it written in there. It's unnecessary. It's redundant. It's like writing x to the first power. Okay? So you're often going to see it written without the base there because we already implied that the base is e. Okay? So if you see ln, you know what the base is. It's e. And the reason we do that is because now this is like something you can type into the calculator. Okay? So for the next one, we have e to the 7th power is equal to x. So now we're going to convert it once again. It's going to be ln base e of what? Of x equals 7. So that's how you would convert it from exponential to logarithmic form, just like before. And once again, like I said, you don't have to write the e in because it's redundant. Okay? Now we're going to go the other way around. We're going to go from ln logarithmic form to exponential form. So you remember how I said if it's ln, the base is e, and all the other log rules follow the same way. Okay? So remember the arrow method I was telling you guys about? E to the 2.1438 power is equal to what? X. Same thing over here. I can write in the implied base, which we know the base to be, and then I can use the arrow method. E to the power of x is equal to 18. So that's how we convert back and forth between the two. Okay? And here's the reasoning we have to do that. Sometimes if you want to solve for a variable, see how we have a variable as an exponent here? There's no other way to solve it other than to convert it to a logarithm. So that's the reason we use this. All right, that allows us to solve for missing variables as exponents. All right, so let's go ahead and actually use these, figure out how we can actually use these to solve for missing variables. So let's say we want to solve for x here. Just like everything else, if we want to solve for x, we got to try to get what it's to the power of by itself. So we got to get e by itself. So what can I do to get e by itself first? Add 5 to both sides. So I'm going to start by adding 5 to both sides. And then what would I do next? Divide by 4. All right, is everybody with me on how we got here? Now, we don't have a way mathematically to solve for x other than to use a log because our variable is in the exponent. So this is where the log comes in. We're going to convert this into logarithmic format, just like we did earlier. Okay? So it's going to be ln base e of 2 is equal to negative 2x. So I converted it from exponential to logarithmic form. Now, do we need to write this base in? No, because it's implied. The calculator knows when you use ln that the base is e. And then what would be my last step to solve for x? Yeah, we got to divide both sides by negative 2. So this right here would be what we call the exact solution. but we can get a decimal approximation by putting it in the calculator. So I'll talk you through how to do this. If you have the 86 or the 36, the nicer calculator, it might be a little bit different. You guys know where the E button is, regular E to the power of, because you've done it before, but you should have a button that says ln on it, okay? So on your calculator, you're going to find the button that says ln, all right? And you're going to do ln of 2, enter, and then divide that by -2. And when you do that, you should get this decimal. We're always going to round to the nearest 10,000 unless it's money or we say otherwise, okay? So let's talk about what this means. We just found an approximate value for x. So just so you guys understand what this all means, if I were to take this x and plug it back in here, if I were to put e to the power of -2 times this value, that's going to give me approximately 2. We just figured out what exponent would make this statement true. Okay, that's the math that we just did. All right? Okay, so for the next one, letter B, I think I'm going to have to scoot it over here. Step 1 is to get the one with the variable by itself. So what are we going to do first? Add 12. Then what? Good. Now we have our variable in the exponent, so we're going to have to convert it to a log. But it's going to be the natural log because our base happens to be e. So we know we use the natural log when our base is e. So ln base e of 9 is equal to what? Good. I don't know why I was putting, that's not right. Now you're going to drop the e because it's unnecessary, and the calculator won't have it on there. And then to solve for x, of course, you're going to divide by 4, and you get x is approximately equal to ln of 9 divided by 4 in your calculator, and you should get this. Alright, so the cool thing about this test, this quiz, this section, if you have extra time on the test and you haven't done it already, you should be plugging this back in here. You should do e to the power of 4 times what that value is and make sure it comes out to be approximately 9 to make sure you got the right value, right? So the cool thing about this is you can verify that you have the right answer. Does anyone in here not know what I mean by that? Okay, just making sure. Okay. So this one here, step 1 is if we want to solve for the variable, we have to get what the variable is contained in by itself. So what do we got to do? Divide by 5. I'm going to leave it as 8/5 for a little bit. Alright, so here's the problem. We can't put an x in the calculator to do ln of 6x. So we're going to have to convert it to what? An exponential form. So whatever way is going to help you get that missing variable is what you're going to use. You can convert back and forth between forms. Whatever one's going to be able to get you that answer. So what you're going to notice is let's convert it to exponential form. I'm going to write the base in, and I'm going to use the arrow method. E to the power of 8/5 is equal to what? Good. Now if we solve for x by dividing by 6, right? See how switching it to the other format on this question was more beneficial and allows us to solve for the variable. So you have to use whatever version is going to allow us to solve for that variable. So I know that the fancy calculators are a little bit different. If you have e, you find little lowercase e, you're going to put that to the power of 8 divided by 5, close the parenthesis, and then you're going to divide whatever that amount is by 6. And you should get approximately this. Okay? So what that means is, if you wanted to check your work here, you could do ln of 6 times whatever this amount is. So you could do ln of 6 times 0.8255, and you should get about 8/5. Alright, so you can also check your work the other way around too. Alright, now that we've got the hang of it, we'll go through this one a little bit quicker. Step 1, I got to get what the x is contained in by itself. Step 2 is I see that I have a variable inside of my ln, so I'm going to have to convert it to exponential form. Step 3 is to get x by itself. So this would be what we call the exact value. And the approximate value would be whatever this is if I plug it into the calculator.
Can I have Ryan talk?
Who?
For a few minutes, Ryan talk.
I don't have that student. Maybe it's with the other Miss Russell?
Okay, do you know where?
Yeah, she's in building 13, the second door on the right.
Okay, thank you.
You're welcome. All right, second e to the power of 8 divided by 4. And you should get approximately 745.2395. So any questions about that? Okay. Next. You already have notes on your desk. Everybody has notes on their desk too when they come in. So the question says a spacecraft can only attain a stable orbit 300 kilometers above the Earth if it reaches a velocity of 7.7 kilometers per second. Suppose a rocket has a mass ratio of 25, a firing time of 100 seconds, and an exhaust velocity of 2.8 kilometers per second. Use the formula below to find if the spacecraft attains a stable 300 kilometer orbit above the Earth's surface. So, basically, we can only attain a stable orbit if these two things are true. Okay, one of these things is true and then the other must be. So what we're going to do is we're going to plug in the information we have about our rocket to see if that's the case. Okay, so we know what R is. We know what the time is. And we know what the velocity c is. Okay, and that will allow us to find what the v is, the actual velocity, okay, versus the exhaust velocity, of course. So we're going to plug in what we know into it and then verify if this is the case or not. Okay. Now, one thing you want to be careful of with these kind of word problems, notice that all of these are in the same type of units. Okay, so kilometers per second, kilometers per second, kilometers, seconds. You want to make sure none of them switch to minutes or like another unit, because you'd have to convert them all to the same unit. That would be a harder problem for sure, though. But just a reminder, something to think about. So T is 100. C is 2.8 times ln of 25. So any questions about that part? All right, I'm just going to do this calculation first. So what I'm going to do is I'm going to do this in my calculator, get a value, and then I can do this part. So negative 0.0098 times 100, bless you. That gives you negative 0.98 plus this. And remember, order of operations says I have to do multiplication before I do the addition. So I'm going to do this part next. And then I'm just going to leave whatever that is in the calculator and then add this to it. And I'm getting 8.0329. And that would be kilometers per second. So that's my velocity. All right. So now that I've got the velocity, I need to figure out if this spacecraft would attain a stable orbit. So let's read the question. A spacecraft can only attain a stable orbit of 300 kilometers above the Earth if it reaches a velocity of. Did we reach that velocity of 7.7?
Yes.
So would it attain that stable orbit? Yes. Because this is greater than this. Okay? So any questions about that type of word problem? Okay. Next question. So all of you remember this old formula here, PERT? We're going to use it again because now we have more skills that allow us to solve for more things. All right? So I'll just quickly remind you guys what this formula means, how it works. A of t, A, however you want to call it, is going to be the final amount of money or amount of something. P is the principal or the initial amount. R is the rate, and T is time. Okay, so that's what all of those letters represent. All right, so as we go through the problem, we're going to identify those. So it says when Angelina was born, her grandparents deposited $3,000 into a college savings plan. If they deposited that amount, what letter represents that? P, the initial. Okay. Paying 4% interest, that represents the, but I have to put it as a decimal. And then how much money will be in the account? Of course, compounded continuously. Remember, we got to look for that. How much would they put in the account or be in the account after 30 years? Time. So what variable are we solving for in this particular problem? A. So A is equal to P times e to the power of the rate times time. So you have the option of typing this whole thing into the calculator all at once, or you can do e to the power of this stuff times 3,000, whatever you feel more comfortable with. So 0.04 times 30. Don't forget when you put e to a power to close the parentheses. And then that's going to be times 3,000. So you should get 9960.35. So think logically through the problems. You're good. You can toss that. I have notes on your desk for you. So.
Did I get that?
What?
I got like 936.7.
So you probably didn't do parentheses around this, or maybe you missed a 0 here. So go through and try it one more time. Make sure you put parentheses around the end of the power on the e. So when you get a problem like this, make sure the answer makes logical sense. If you are gaining interest, your amount is going to be greater than what you started with, right? So make sure that that's the case, all right? Just verify that. And the reason I rounded to the hundredths place is because we're talking about money. So with money, we always round to the hundredths place, unless it says nearest dollar. So if it says they could only deposit $10,000 in the account above, if they could only deposit. So what amount or what letter does that represent? P. At what rate would the account need to grow in order for her to have 30,000 represents what? A, because we want the account to have that amount at the end. 18 years is represented by T. So what letter are we going to be solving for this time? R. So we need to find R, okay? So we're going to plug into our formula. A is equal to P times e to the power of 18R. So what you're noticing now is we're trying to solve for one of the variables that's in the exponent. Does everybody see that? So that's why we have to use these new tools we've learned about in the last lesson or two to be able to do that. So step one is to get the e, the thing that contains the variable we're solving for, by itself. So I divide both sides by 10,000. That gives me e to the 18R is equal to 3. So does everybody see how I got that? Okay. Now, what's the method we use to solve for when we have a variable in the exponent? We use the ln, the natural log, right? We're going to convert this to logarithmic form, okay? So it's going to be ln base e of what? 3 is equal to what? 18R. So we're converting it from exponential form to logarithmic form. And remember, because the base is e, we use ln instead of log, okay? When we use ln, we imply that the base is e. The calculator knows it's e, so do we need to have the e written there? No, it's not necessary. And then what would be my last step to solve for r? Good, divide by 18. So r is approximately equal to Now you can do your calculator calculation. So it's going to be ln of 3 divided by 18. And you should get 0.0610. So that would be my rate. And this rate is represented in decimal form when it comes out of the formula. But how could I convert this to a percentage? Two decimal places. So it's 6.1%. So the growth rate would have to be 6.1% for them to achieve the goal that they're looking to achieve with the money. So do we have any questions about that? All right. So the next one. If Angelina's grandparents found an account that paid 5% compounded continuously, so we take that rate and we convert it to a decimal, and wanted her to have 30,000, wanted her to have, that's A, right? After 18 years, how much would they need to deposit? What are we trying to find? P. We need to find P. So we're going to plug in for everything except for P because our goal is to solve for P. So that's going to be A equals P times e to the power of r times t. Your goal is to solve for P, so we divide by e. We get P is approximately equal to, I know P is going to be money. So in your calculator, the most important thing when you do this is you have to put parentheses around the exponent on the e. So 30,000 divided by second ln on my calculator, yours might be different, 0.05 times 18. Oh, I messed it up. And you should get 12197.909. And that makes sense, right? Of course, the principal is not going to be as much as the final amount because we're trying to gain money. We want to see how much we had to invest to get our goal, to reach our goal. So does anyone have any questions about that? And like I said, if you're having calculator troubles with yours and you need some help and assistance, I'm happy to do that at the end if you guys need it. All right, next. So it says, determine the value of K, Georgia's relative rate of growth. Okay. In 2007, the population of the state of Georgia was 9.36 million people. And in 2000, it was 8.18 million. So we're talking about K, where it says K is relative rate of growth. If we take our original formula, like this formula usually represents money. Sometimes you're going to see this formula instead written like so. So this formula, you'll also see it in disguise as this. Let's tell you what I mean by that. Okay, so like sometimes on SAT or something, they're going to write the formula in this format instead. Okay, so R is your rate, K is your rate. P represents principal, little a represents the initial amount. It's confusing because it's both A's. But remember how little a in the formula y equals a times b to the x also represents the initial amount? So you've seen that happen before. Okay, and y, you know y is the final, same as like with regular like xy. So I just want to be clear, it's the same formula, they just use different letters to represent the same thing. Okay, so in 2007, the population of the state of Georgia was 9.3 million, and in 2000, it was 8.18 million. So which one of these is going to represent the starting amount of the population?
8.18.
Yeah, 8.18. Okay? Because that's how much the population started with in 2000. 2000 happened before 2007. So the starting amount was 8.18. Okay? Y represents the final amount. So what's the final amount of data we have for population?
9.36.
Good. Okay. We don't know what the rate k or r is, but we do know how much time has passed, right? 7 years, right? So did everybody see why t is 7 there? Okay. So now we can work backwards to find what k is. So 9.36 is equal to 8.18 times e to the power of 7k. We divide both sides by 8.18, and we get this. And now we're in a situation where we have e to some power is equal to some number, but e has a exponent that has a variable in it. So immediately when we see that we have e with a variable as an exponent, what do we got to do? Switch it to a log. Good. So it's going to be log ln, because we use ln when the base is what? E. So if the base is e, you're going to use ln instead of log. Now it still would work with log, but anyways, that's a whole other story. So ln of whatever it's of is equal to whatever the exponent is. Divide both sides by 7. And k is approximately equal to. So in your calculator, hit the ln button. Ln, it says ln on it. And then you're going to type 9.36 divided by 8.18 and close the parentheses. And then you can hit enter. And then take that amount and divide it by 7. So that's going to be 0.0193, which converted to a percentage would be 1.93%. So now we just figured out what the rate of population growth is using 2 pieces of data. Okay? Now we can apply that to future scenarios, right? So for the next problem, we want to know when Georgia will reach 12 million people. We already know what k, the rate, is. But remember, when you're plugging it into the formula, you want to use the decimal version, not the percentage. What letter does 12 million represent in the formula? Y, because it's what we want it to be. So when? We're trying to find, if we want to know when, we're trying to find what? T. We want to know what T is. So we have enough information now to plug into our formula. So 12 is equal to, oh wait, we forgot one thing. Little a, we already know what little a is, right? The initial, which is 8.18. The initial population.
Why don't you add all the zeros? The 12 million.
Oh, good question. You only have to convert them to actual like full numbers if they're not all millions. So if one of them was like thousands. So if they're all millions, it's easier to not convert. It's like going to save you all the work at the end. But if you want to convert it, it will still work. So it's going to be times e to the power of k times t. So we divide. We get this. Whatever that is. Now I have a variable in the exponent, so what do I got to do? Switch it to ln, convert it. And then solve for t. So do that all in the calculator. I do the ln part first. Ln of 12 divided by 8.18. Close the parentheses. And then divide it by 0.0193. And you should get about 19.8557. But let's like read the question again. It says when. Does 19 point something tell us when something happened? No, so we have to think logically here. This formula is all based on original data that occurred in what year? 2000. So if from 2000, 19.8 something years have passed, what year are we in now? We're not in 2019 because we went past 19, right? So we're actually in what year? Does everybody see why it's 2020? Because this part represents 2019, and then if we exceed that at all, we're pushing into the following year. Does everybody see that? Okay. So any questions? All right, I'm going to have you guys try this one on your own, but I want you to be very careful. Before you guys do, though, wait, I got to tell you something. When you read this question, it doesn't say increase or whatever. It says depreciate continuously. What do you think you're going to do to your rate here?
Decrease.
Make it negative. So when you do the rate, you got to make it negative, okay? So you guys go ahead and try that out.
Isn't this what we did like 2 units ago?
Yes, which you're going to be tested on, so it's good at reviewing. But the reason that we have to address it again is earlier, now you can solve for when the variable's in the exponent. You couldn't do that before.